right, let's do this example problem on shear and moment diagrams right here. And we got this beam that's pin supported. It's got a distributed load in this first third of 2 kip per foot. And then 30 kips concentrated at this point right here. And then point B is a pin support and point A is a roller. Each span is, or this is 5-foot intervals, if you will, 5, 5, 5. And the way we're going to do this is, let's see, our approach real quick is going to be 1, calculate reactions, 2, then draw the shear diagram, draw shear diagram, and we're going to do that graphically. So we're going to, important relationship going left to right, dv dx is minus w, and then 4, draw the moment diagram. And this moment diagram, that relationship is going to be dm dx equals v, also going left to right. And now we're going to calculate some reactions. So you can skip this if you're good at calculating reactions. Otherwise, calculate some reactions. So let's see here. Calculate reactions. That's an x. X factor. Okay, no. But here, a, y, by, bx. Okay, don't be ghetto. Make a good drawing. Use a straight edge. Right? Pass the FE. All kinds of other things. Okay, but here, so calculating reactions, I would say the best thing to do, automatically some of the forces equals 0 plus to the right, and bx equals 0. That's a no-brainer. I think the fastest way to solve for these reactions, AY, BY, are just to do sum moments about various points. So here, if I sum a moment about A equal to 0 here, positive, then I would have, let's see, this resultant is 10 kips here. The area of that is 10 kips. And so I would have, let's see, 10 kips times 2.5 feet. And this, I'm doing moments about A minus 30 kip feet plus by times 10 feet equal to 0. And that would tell me I have, let's see here, this is that 2.5 times 10 is 25. That's 25 kip feet minus 30 kip feet plus by times 10 feet equal to 0. And that tells me by is 0.5 kips. And then I calculate, I can use either equation. I could take moments about B or just some forces in the vertical. So I'll just sum forces in the vertical here. Equal this way plus, and I would have AY plus BY minus 10 kips equals 0. And that tells me that AY is equal to 9.5 kips. Yay. Okay, congratulations. You have passed one question in statics. All right, but here, let's move on now. Now that you have it, one thing you want to do, this is like a mechanical process, if you will. You want to make a drawing with your whole beam, okay? So hopefully you're doing that right now as you go. Maybe you're even like racing in front of me, right? It's like a race, okay? But you want to draw, if you're practicing this as you're watching the video, which I highly recommend, make it like a race, you know what I'm saying? But here, I'd have, oh gosh, I'd redraw this. So I want to redraw this. This is kind of a step that no one ever really mentions, but redraw with reactions and loads. Okay, so that you can have a clean drawing. Use a straight edge, be an engineer, right? And here we're gonna redraw this. So bam, then bam, and bam, bam, and bam, like that. And I have, let's see, I have a distributed load here of 2 kip per foot. I have a reaction here of 9.5 kips, a reaction here of 0.5 kips, and a concentrated moment here of 30 kip feet. And let's make sure that I did that correctly. Yes, I did. And here, my dimensions are as they're still the same, obviously. And here, boom, boom, boom. 5, 5, 5. It's like a Herman Cain plan. All right, so 555, right? Anyway, so here, except it was 999, but anyway, that's blah blah blah. Okay, who cares? All right, so here, now we're ready to draw the drawing, right? And so the thing to do, you've probably done this quite a bit, is draw using a straight edge some lines, okay? And so, bam. And really, the thing to do, the place to draw these lines, to draw lines at discontinuities, okay? Discontinuities. And what is a discontinuity? It is wherever the at beginnings and ends of distributed loads, okay? At concentrated forces, at concentrated forces, that includes this subheading includes reactions, okay? Because this reaction right now, as far as we know, is a concentrated load that's pushing up on the beam right here. Reactions, and then at concentrated moments, okay? And that'll do it, okay? That'll do it. So if I look here, I have the beginning of a distributed load, I have the end of a distributed load, plus a concentrated load there. So I'm going to draw a line there. And then I've got a concentrated moment, and I have a concentrated load here, bam, or a reaction. And so then this will be my shear diagram right here. And I don't really know what that's going to look like yet, but we will proceed from there. And I will have a moment diagram line. I'm going to give myself some space and maybe go right about here. Oh, what the heck happened? My line shifted a little bit. Oh man, don't judge me, judge yourself. Okay. And here, this will be units of kips and kip feet. So always label your axes. And technically speaking, this is the x-axis. This is along the length of the beam. Okay. So here, so hopefully, starting for the shear diagram, you have, technically speaking, right at this point right here, if I could zoom in right there, I have this cut, and there's no distributed loading yet, so my shear that would be here is actually equal to 0, right? Otherwise this thing would be moving and all that. So I start off, I know that this is 0 right here, bam, 0. And then because I know my relationship dv dx equals minus w. This w is 2 kip per foot, so I'm decreasing at a slope of 2 kip per foot. So negative 2 is my slope here. Bam, negative 2. And my change in shear is equal to the area under the distributed load, which in this case is this area right here, and that area is 2 kip per foot times 5 feet, which is 10 kips. And so I would go down at a rate of 2 kip per foot all the way down to 10 kips right here. This would be minus 10 kips. Okay, I feel like I've done this example somewhere. I've done so many stupid shear moment diagram problems. This looks really familiar, all these numbers. Anyway, then I have here a concentrated load, and really, as long as I have this going left to right, I just follow the direction of that concentrated load. And so I'm going to go up 9.5 kips, and that's going to take me to 0.5 kips. And this is probably not to scale, but that change right here is 9.5 kips, which gives me a value here of 0.5 kips. And I'm going to go straight across, bam, right there. And really, my concentrated moment does nothing to my shear, so I keep going straight across all the way over right here. And then this 0.5 kips pushes me back up, if you will, but that's going to be 0.5, negative 0.5 kips right there. And so your shear diagram will look like that, essentially. Now we're ready to do the moment diagram. And in this moment diagram, which, let's see, can you see orange? Now, how about purple? Let's use purple. So dm dx equals shear. So the slope of my moment diagram is equal to the value of my shear. The other thing I have here is that my loading here is a uniform. It's a constant. So I like to put a little notation. This is constant. I have zero loading in these regions, okay, between discontinuities, if you will. And so here I know that this, the antiderivative of a constant, is a linear function, or is a function of x. And this right here, antiderivative of x, is going to be x squared, right? And then same thing here. This is going to be a constant, which it is, constant. And then I expect that my moment diagrams here will be linear, okay? All right, that's good. Okay, so now I also know that here, if I go back to this little joint right here, this moment, because I have no loading here on this joint, this moment is 0, so I know I start at 0 here. Okay, and in general, when you have a free end, you're always going to start at 0. Okay, this is a free end. So you start from 0 here. And you know that the change in shear in moment, the change in moment is equal to the area under the shear diagram. Okay, the change right here. And so I have this right here, this region right here, the area of this is 1/2 base times the height of this area right here. So that's going to be 1/2 times 10 times 5, which is 25 kip feet. And because it's a negative area, if you will, it's below the curve, I'm going to be decreasing down from 0 to -25. That's going to be -25 kip feet. And now I have a choice. I know that it's parabolic. When it's parabolic, I know that I can either be going like this, or I could be going like this. And the way you know which diagram it is based on the slope, this relationship here, okay? And here, the value of my shear is 0, so the slope of my moment diagram at this point should be 0. Yeah, 0. Oops, and the wrong one got erased. Shame on that one. Okay, so how do I get rid of that? I need to get rid of this. Bye-bye. Bye-bye. And so the correct drawing, if you will, should be like that. And that should have been parabolic, x squared, like this. Bam. Okay. Then I have, what's more, again, this area over here, and you know, it's like, what the heck? It's constant, so I know my graph is going to be linear now, and the change here, this area here is let's see, 0.5 times 5, so that's 2.5 kip feet. Bam. So I'm going to decrease even more, 2.5 kip feet, and it's going to be linear, so I know, and my slope, the slope here is 0.5 kip per foot. So the slope here, this is, I guess, an important point right here, is this slope right here is the value, because it's constant right here, this slope right here is -0.5, or it's a 0.5 kip per foot slope, if you will. Okay, and so this number right here, the change going from here to here, it should be 2.5 kip feet, and that means this number right here is -27.5. Okay, I don't need to put units because I put the units on the axes over here. Okay, and so here I have that. Now, the thing that people run into with the concentrated moment is when it's drawn like this is, do I jump up or do I jump down? Okay, there's a concentrated moment, there's going to be a shift up or down. Okay, and really you could go through the deal of making a cut on this joint, like you could isolate this joint right here. You would say, I've got this concentrated moment at 30 kip feet. Over here I have a -27.5, which is actually a moment going like this, -27.5. This is 27.5 right here. And then what's the moment on the 30 kip feet right here? Okay, but what's the moment here? What is this moment value, right, to maintain equilibrium? And you would say that, oh, based on this right here, the moment value on the other side of the concentrated moment is actually supposed to be 30 minus 27.5, so because I have to have equilibrium of the joint, is 2.5 kip feet. And you would say, oh, this value right here should be 2.5 kip feet. Okay, that's one way to do it. The way I do it, which is a little, it's just like a rule of thumb deal, is I actually erased this right here. And really what, this is like my own little rule of thumb, and it's tested and it works, okay? And if you're going left to right, what I would do is instead of drawing the concentrated moment on the right side of the point, draw it on the left side of the point. Okay, so this arrow is the exact same thing as what I had before, which was this. Okay, that means the exact same thing. And if you draw it like this, that you'll see the arrow points up, if you will, right? And that means you should jump up 30 kip feet. So I would say this distance right here, this distance from here to here is 30 kip feet. Oh, I know this is getting sloppy. Okay, my apologies for that. And then I have the rest of this right here is going to be that it's also 2.5 kip feet, and I'm decreasing again because I have a negative shear value, and I end up back down to 0. And hopefully I can draw that. Bam, like that. That should be a line to 0. That's 0 right there. And here's that 2.5 kip feet. And so my moment diagram looks like this. I'm shading it in so that you can see it better. Maybe right here. There's that moment diagram here and here. Bam. Okay. So hopefully that was an explanation and worked for you. Enjoy. Don't forget to keep your units. Label your axes. Be anal retentive about that kind of stuff, right? Because it's all about credibility, man.